Okay. Dear friends, in today's edition of the ABR library, we are going to cover the set of the big studying essential questions. Because under ABR umbrella, we cover the whole spectrum, right? The usual, the big three. So the first would be the brain injury and the related diagnosis of cerebral palsy. Second, genetic conditions and the related label of the rare diseases. And then, of course, you've got the part which doesn't have a particular label and just goes under the general developmental delay. Of course, the natural question that comes up, how come that you guys cover all these things at once, and somehow what's the kind of common ground between all these approaches? So, that would be the centerpiece of the entire approach, child development and rehabilitation, right? And there, this term itself, child development, already points out to the common thread, right? The common denominator that we are going to deal with and that we are going to address. That effectively all these components, they eventually plug into the child's development process. But now let's get some clarifications and answer the most difficult looking questions. So, to help you with this, I've made this very simple graph consisting of 4 parts. The word DS stands for the diagnosis, and respectively along the y-axis we have the neuro, along the x-axis we have the genetic. So let's start with something more familiar. Here we are in the neuro department. I've also added this kind of additional clarification in the form of this triangle that is supposed to indicate the level of specifics. Because what happens, right? So, for example, you get the situation like complications of the child's birth, or the complications of the development in certain months of pregnancy, or the complications post-birth in the hospital delivery and so on, and then via a set of challenges, whether it's asphyxia, right, lack of oxygen, whether it's something else, whether it's some, the vascular accident in the brain, we end up with a certain situation which goes under the label of the brain injury. But now, the brain injury can vary in terms of the specifics and depth. Right? Specifics, that would be a very particular neuroanatomy, and sometimes you do have the cases when, for example, the child has that just malformation, a certain part of the brain just kind of apparently, if you look at it anatomically, didn't form or was specifically damaged. And of course the next level is the depth, because more often what happens is this kind of broad situation. There's a certain region which is being affected, but it's hard to pinpoint exactly, right? So, and then it could be, on top of it, it could be the certain even level, like for example, like leukomalacia, right? So you see this type of things when you get some troubles with the formation or with the proportion between the white and gray matter. So there could be all sorts of the combinations and variations, and what interests us is that point that is the thing that happens at some point near birth, right? So that's this entire spectrum. Of course, the natural question that comes up and that requires an answer is that, okay, we have the map of the brain, or the, technically speaking, the neuroanatomy of the brain. I'll draw it this way, right? So that means that you've got the brain and it has different levels, right? The stem, the subcortical, the cortical, and then it has certain proportions within it between the white and the gray matter, and it has its own lobes, divisions, and so on. So in certain situations it's possible to pinpoint exactly and say, hey, that's a certain part of the brain that is really anatomically damaged, and you see there is no particular life there anymore. And then around that area there will be certain next area where it's a kind of, if you speak of black and white, so if this is black, and then you are going to have some kind of gray area, right? So that's also the part which comes in. So, but the overall message here, you've got the neuroanatomy, and neuroanatomy rules different body parts and systems. So the logic is, if there is something wrong with the neuroanatomy, it gives us wrong signals, and those wrong signals then translate into what? Translate into the wrong performance of this controlled body part. So that means that the wrong functional performance and poor formation of this body part, of the controlled body part. So that's more or less the logic, right? So the most typical logic here, a certain area of the brain, especially if it's following the lack of oxygen, you get the certain loss somewhere within the cortical levels, which in turn translates into the wrong signals going to the muscles, translating to the spasticity, which in turn eventually translate into the poor performance, which staying for a certain period of time and creating the wrong tendencies. So the structure adapts, so the structure gets poor as well, right? So you see here we get both function, tissue, and structure. All of them gets affected. But now, of course, that's the example, say cortical, but it could be brain stem, right? So you see, it could be hippocampus or whatever. It could be some specific area where, in case of the cortical levels, it's much broader, right? You can't really pinpoint so much, right? It just generally say the superficial muscles. But the deeper you go towards the brain stem and the subcortical structures, the easier it is to get some pinpointing things, right? So and then you can get exact labeling and say, oh, you know what, this is the person has problems with balance and he's ataxic because he has this particular damage at the level of the brainstem. So these kind of things, right? So that's the question that naturally comes up. But when we want to answer these difficult questions, we don't stop here. We move further, right? And then, you see, here we started with the neuro, and then we arrived to the functional, structural, and the tissue level trouble. But this way, we also have another set of troubles, right? So that would be the genetics. So, when it comes to the genetics, what do we have? We have usually certain trouble which belongs either to the tissue, right? So I'll move to the corresponding page. So if it belongs to the tissue, what does it mean? That means that genetics are responsible for certain problems with encoding, say, a particular protein, and if this particular protein is not encoded, then you get the tissue which is becoming too, the elasticity is insufficient, means it gets too tight, or on opposite, it has a very low coefficient of elasticity, so it's easily stretched, or a certain part, whatever, of the fat breakdown tissue or fat breakdown cascades is not working, so it's tissue level. Plus, of course, that tissue thing comes into the periods of the development, so it corresponds to some specific period. So therefore, in the well-known conditions and the widespread conditions like, say, Down syndrome, you're also going to have corresponding specific structural features, right? So it's going to be structural according to the embryonic phases. But then from these tissue levels, you see, remember, these are the people without any neurological diagnosis, right? So you see that these rare conditions, they don't have any particular damage to their brain. But then what happens from the tissue level, because the tissue is problematic, you eventually get the problems which go all the way up to the what? Functional and structural levels. So functional and structural. And again, this whole thing could be quite variable, right? In my previous drawing, what I did this type of the triangle, pointing out that at the base there are widespread, relatively widespread conditions like Down syndrome or Rett syndrome. And then at the top here, there is all kind of this very rare conditions which have only been detected maybe in the last 10 years, right? We remember that the human genome has been decoded in the year 2000, right? So it's 20 years. So therefore, before that, most of the conditions which were defined, they were probably mostly, the chromosome defects, and now it could be a lot more diverse what could be identified, right? And that's why in the last 10 years, there are several hundred specific conditions, each of them having anywhere from 50 people to maybe 2,000-3,000 people around the world. And these numbers are going to increase. So the question that comes up here is very obvious, right? Is that since the problem belongs to the genes, right? So you see, to the basic tissue level encoding, right? Then obviously the natural question is, well, how do you guys plan to improve the situation? Because here we've got the tissue, right? The tissue defects, they translate into some structural issues, they make certain functions impossible, so therefore, if that is the level, well, the natural question is, well, what do you expect? Do you expect to correct the genetics in order to help this person? And that is obviously impossible, right? So the question here is equally impossible as the question here, right? Because here is the question of the cure for the brain injury. So these questions are equally impossible. So if these questions are equally impossible, then quite naturally, you get to the point of how do you guys plan to deal with it, and how do you plan to get anything positive in terms of the child development and rehabilitation. So, see, we didn't just put ourselves against one hard question, distributed brain injury towards the very specific brain injury or missing part of the neuroanatomy. We brought ourselves to the two equally difficult questions. Now we came from the point of the tissue, linked it to the genetics and said, well, not only that, but there is this question of the genetic and the malformations or the troubles at the level of the tissue, that they could be brought into the picture. So let's assume, so we took this quadrant, and then let's assume some dramatic situation that the person not only has the brain injury, but the person also has the genetic condition. Is it possible that a person with a genetic condition gets the brain injury? Yes, it is possible. So let's, in order to be able to give a true and fair representation to our approach, right? So let's make the darkness even darker, and instead of one of each, let's put two together. So, in that respect, let's put the specific brain injury, like certain easily identifiable loss of neuroanatomy, plus let's add some kind of general asphyxia on top of it, and make it into the distributed neurodeficit as well. Right? So therefore, in that respect, we're going to get it in two levels: neurodeficit and neurodamage. Both. And now here we are going to get it to throw in the next point, right? So the tissue malformations. So the difference between the two is that here we're assuming that the neuro damage, it was the once in a lifetime, and here you've got the fundamental processes. See, that's the kind of renewal processes. See, this happened at birth and then left a damage and left a lasting effect, so the system has to adjust, right? And here you know, this genetics, it's a renewal that happens all the time, right? So that's the difference. So now we have created, you know, put two darknesses together, this darkness, and even from that darkness made it even darker. So that's the situation that we are looking at and asking ourselves a question, how this particular person could be helped. Before we get there, let's kind of bring a ray of light into this thing. So what do we actually observe in reality? In reality, it's interesting that we observe a lot of cases where, from any practical perspective, if we just observe the individuals, the general difficulties, the general developmental difficulties between the very different diagnoses, right? So you see that's the genetic diagnosis, and that's the diagnosis which is neuro. But surprisingly, if you just look at a whatever 1, 2, 3, 4, 5-year-old child with developmental difficulties, you'd have hard time telling, is it the child with the brain injury or is it the child with the rare genetic condition. So that's a first point that we can actually see that in fact when it comes to the developmental difficulties, there is a lot of similarities. Similarities. Not the difficulties, but not the, we're not even looking at the difficulties here. We're talking about the similarities. There's something in common. And at first point, it looks really strange, right? So this is one diagnosis, has to do with the biochemistry and the tissue composition. This is a completely different diagnosis, has to do with the neural control and has nothing to do with the tissue composition and the tissue, production at the biochemical level. But if we look here, the effects are very similar. So, in that respect, that should be an inspiration for us and potential, clue to finding how it works. So, once we realize this, then we just get to the next level. And the next level is going to be represented like this. So, what we have here are two big blocks. So, what we are going to look at, instead of the narrow definition of the brain and neural control signals and so on, we are going to look at the much broader definition of the control functions. And here, instead of the narrow definition of genetic encoding at biochemical level, we will be looking at the much broader definition, which is going to be the tissue, technically speaking, the tissue homeostasis, right? So you see that's the maintenance and renewal. So that's what we are looking at here. And now, with these two big points, is it possible to have the damage? Yes, it is possible. You know, the damage to the neural thing. Is it going to make some negative effect to the control functions? Yes, it's going to do. Now, is it possible to have the defects at the biochemical levels? Yes, it is possible. Is it going to affect the tissue quality, production, and the way how it's, performing its maintenance and renewal? Yes, it's possible. But that's a trouble diagonal. Now let's look at the things which are going to help us overall. So first point that I'm going to put here is going to be the point of general vitality. So that will be kind of internal. In simple words, we ask ourselves the question, how much help does this person need to survive? So, of course, there are situations when the person requires continuous type of the support in terms of the, blood transfusion, artificial lungs, and all kind of these things. So, and artificial feeding. So, of course, that's a situation when the general vitality is very low. But what do we see? We see two things. That for a great number of children, once they are out of the acute crisis phase, there is a certain more or less functional balance of this internal general vitality. There could be troubles with feeding, there could be trouble with what they're digesting, and so on and so forth, but generally they are self-breathing, they are self-surviving, they're kind of self-digesting, and so on. So generally, the big systems of the general vitality, they are functioning. And the good point is that once these systems are functioning, that means they're also compatible with the tissue renewal, right? So that people are living through, so there is a formation of the new proteins and it's going on. So therefore these systems of the general vitality and the general maintenance, they are functioning. So that's already a very big thing to begin, to start with. Second point that we are going to bring in here is this. Now, the second point, from the specific control functions, right? Dedicated control functions. Then we move and ask next kind of question. Dedicated control functions, central. Once we start deconstructing it, we ask ourselves the next question. Well, yes, are there dedicated, designated, specific control functions? Yes, there are. But next point is, since we have this vitality, generally in place, then we ask the next question. How much of the transferable global central functions are there? What does it mean? That's what goes under the label of plasticity and redistribution. So all we need to know about the control functions is that as long as there is some transferable potential within the global central functions, there is plasticity and redistribution, which is significantly greater than 0, we are already in the game, right? So you see, if the total control function is 100%, so what we know, out of this 100%, a certain part is gone. But we still have quite a lot left. First point, within the central functions, how much is transferable around, right? So you see, if we were to draw this brain and this was kind of gone, then it's the question of how much could be transferred around and distributed. And then, of course, the next question is how much of the control functions belong to the periphery itself, right? So you see, because, right, we were back here to the function, tissue and structure. So how much of it is in the structural control functions? So what does it mean? It's actually quite a simple thing. You know, the more stable is the architecture, the less of the specific and active control the system needs, right? So you see, in other words, if I try to put, I don't know, this pillow on top of this pillow, and the architecture is poor, I have to exercise a lot of active control functions in order to keep them one over another, right? So you see, I really have to do all these specific feedback loops and so on to get it going. But if I take something like this, right? If I take something which is well architecturally combined together, then I don't need much of the control functions, right? So because then this system is architecturally and structurally quite well done. So first point is we have that space, transferable and delegated functions. Second question that we have here, now we go back to the tissue homeostasis, right? And say, well, within that tissue there's the same thing. How much of it is, instead of dedicated central, it's the same thing. How much of it is dedicated specific, and how much of it is what? Transferable and distributed. So effectively we ask the same type of question. Dedicated local and transferable distributed. Putting it simply, if you compare it to buildings, my favorite example is this, right? Is that if you have the nice architectural plan and you have the bricks which are all coming together, and then there is the bricks, and then there's another set of bricks, and then the bricks, and so on, and they're kind of in between. So everything is nice, right? And you get the factory that produces those bricks. So then in this scenario, if these are the bricks, you don't need that much of mortar. You don't need that much of cement to put between, because it's all arranged already nice prefab. But if we go to countries like Spain, Italy, France, and so on, what we're going to see? A lot of the old bridges, houses, walls, and so on, they were made out of the stones of the most strange and irregular shape. Now, if we just try to put those stones of irregular shape together, things are going to fall apart. But if we have the architectural plan and we fill up these things with this mortar, right, then what we're going to have, we can have a relatively nice wall that is going to be able to sustain. So these are the standard bricks, standard bricks, and these are irregular stones. So the general idea that we are having throughout this is principle number one is, right, so it's generally it's working. Exclamation points. That's our, not even the principle, that's our kind of foundation. And out of this, generally it's working. What is our basic point? How to make it easier. Right? So if it's working, well, it's already working. It's working harder than a healthy person, and so you got the basic question: how to make it easier? Well, and then we have two lines at the very least. First point is what? Architecture. So if we look at the general mechanics of the body at all levels, then what we are asking ourselves, we're asking ourselves the points, okay, how we can get the entire architecture more favorable, right? Because that's what we saw right here at our example with the bricks. If we can get a better architecture, then even the most irregular stones, you can make the structures, you can make systems which are going to be sustainable for a long period of time. So, architecture always helps. And when it comes to the architecture, what it means, we will look at the elements which are respectively presenting what? The weaknesses, drains, and risks of failure. Right? Then, from the control point, what do we want? We want the same. The more sustainable is the local and regional. So that means that local and regional at mechanical level. The more sustainable is local and regional at the mechanical level, the less you need to get from the controls at the top, right? And the third thing, energy expense. The less of the waste and unnecessary or excess effort and cost, the better. Right? So you see, means that we help to reduce the costs, then we are sure that it's going to make the life easier. So that's the only way to deal with this situation, because otherwise the only thing that you're going to believe in is magic. See, otherwise you need to believe that there is some way of providing the cure for the brain damage or providing the cure for fixing genetics. Both of them are impossible. But at the same time, doesn't mean that the things are having, that the whole thing is helpless. Because once we look at the architecture, and once we look at the distributed controls, and once we look at the energy expense, we understand that all these things together, they link us towards the different properties of what? Of connective tissue. Right, the fascia under the umbrella. So because here we see that connective tissue is about the architecture, right? So if we get back to my example with the irregular bricks, the cement and mortar in my example there, right? So you see that was the connective tissue. Then the connective tissue is about the energy saving, because connective tissue is so simple that it costs a lot less to run than the specific ones, right? And then the third point is about the controls. So connective tissue is globally connecting the entire body. So that means that there is representation and links which are going through what we've heard about the fascia, right? So you see it goes from head to toe and from individual cells to the global levels, right? So you see, therefore, there we have the controls for potential action at distance and for super coordination, and for the organized networks. So that's what we have through the connective tissue as the target that we are able to address, that we are going to look at as the source of the good things. And to complete this foundational conversation, I'll get back to my part 1, right? And part 1 was here, right? The part 1 was here. Was it here? Yes. It was here. We understood that developmental difficulties present a lot of similarities between the genetic conditions and between the neurological conditions. As the specifics of this A1 and A2 they are very, very, very different. You know, this is the neuron, and that's genetics. Completely different scales, completely different levels and so on. But we see there is a lot in common. So that encourages us to say, if these specific things are not showing such a difference in the outcomes, well, that indicates that this part of the B1 and the B2, of this deficit and this kind of components that comes in the architecture, control and the energy expense, that's the part which has a significant impact, right? And it's actually these levels that affect the total outcome more than the others. So that's the general big picture. I know it might sound a bit too heavily theoretical and so on, and like too many steps of traveling from the general problem to how we are going to tackle it, but that's the only way, because otherwise, what you would expect from me, you would expect from me the promise of miracle cure. No, I don't have any promises of miracle cure, I don't have any tools for the miracle cure, but my general point is this, that we have to really develop the first point, the super respect for complexity of life. So that if the person shows general vitality, that's a lot. If the person on top of this shows ability to control and contain certain emotional level and so on, and kind of fluctuations of the muscle tone and some externalization, that's even more than a lot. And if the person shows certain components of movements and so on, that's more than a lot, that's a lot more than a lot. It's huge. So that's where we have to understand how complex is this system of keeping it together. So my point is very simple. This is the system which is not broken. This is the system that we can trust at both levels. We can trust it at the level of the controls, starting from the neuro, and we can trust it in the system of the renewals and the self-maintenance. And once we trust the system, then it becomes simple. Say, hey, we don't have to play God, we don't have to play Lord Almighty, we don't have to figure out how exactly it sort of, specifically step by step it solves it. All we need to do, if we help it in terms of improving the mechanical architecture, if we help it in terms of the distribution of the delegating as much as possible of controls to the periphery and self-organization there. And if we reduce the energy drain, then this big system is going to say thank you, because it's going to make life easier. And somehow, some way, it's going to reorganize itself and bring the child's development into a higher level. So that's really the big picture of the development and the big picture from which I approach the whole, rehabilitation thing. So because in that respect, we are fundamentally bound by this central message. It is that much of life and then growth and tissue differentiation, that's life. And then the therapy is supposed to be some kind of specific catalyst that helps it here, helps it here, helps it here. So it's plugged in into life, right? So you see, in that respect, life is where things are happening, and that's where we plug in. We are not replacing life, we are not playing gods and so on. We are respecting the life and the processes first, and then our part is to make life easier, right? So you see, that is the general part, right? Therapy is making life processes easier. That's what therapy, rehabilitation, and so on is about. That's this level. So that's the big picture from which we start any approach to any condition, and you can see that it's applicable to the whole scope. We didn't try to save and be picky and say, well, this is the particular diagnosis of this, and we deal with that, and this is the particular diagnosis. No, that's medical thing, right? So when people are looking at the specific solutions for some forms of this A1 and A2, for some genetic solutions, for some neuro solutions, they're doing it in the laboratories, they're doing it with the big pharmaceutical and whatever tissue engineering companies, and that's a great job, and I hope that they find those things, that they find the ability to fix this or this and this part of the machinery. But our part, the general rehabilitation part, belongs here. What are the distributed controls and what are distributed architecture and tissue renewal processes? The more we can help those, the more we can plug into the existent life, well, the more we can help. And that makes us capable of helping both the neuro people, the neuro problems, right, the A1. It helps us capable into addressing and improving the development of the genetic and A2, whether it's broad, whether it's narrow, whether it's already known and existent genetic condition, whether it's yet unknown, whether it's general kind of overall cortical, or whether it's a very specific neuro. For us, from that perspective, it doesn't matter. We trust the system, that the system has enough connections to live and renew itself and grow and handle this big chunk of this very complex process. Our part, plug in, make life processes easy.
And do you know why when it's happened wrong on the body,
Yes.
why is the first part that is altered or is the fascia? Do you know why? Or because, for example, there are Down syndrome, or is a cerebral palsy. The first structure that suffer this situation is the fascia, and it's not other kind of structure.
Well, I mean, which just what we, well, that's a good question. Why the fascia suffers there, right? Well, I guess it's exactly for the same reason, because that's the, you see, if you look at it that way, it's renewable, so it's the simplest thing, right? So it's like, it's the most dependent on its architecture. Right? You see, fundamental, if you look at whatever, at collagen or any other structures, so what works there are, you have the formula, right? You have the formula of how the individual molecules are actually composed, right? But the organization of those working molecules, right, is super complex. So it works as a combination of thousands or even tens of thousands of those elements, how they're put together. Now, these are the very fine connections. So when the system shuts down, or when there is some crisis and so on, what are the levels that suffer? These higher levels of the organizations within that fascia. So you see, for example, there is this conversations, well, like, let's put it like this. Collagen. If you boil the meat, the collagen molecules are still there. But instead of being connected, when you look at the gelatin or the jelly, right? The collagen molecules are still there, but instead of being like connected into the things which are thousands or tens of thousands of them together, now it's maybe 20 of them. You know, it's chopped into the small pieces. So the architecture is lost. The same thing happens to capillaries, the same thing happens to everything. So therefore the high level architecture of connective tissue is lost during the time of crisis. And that's kind of polarity there. On the one hand, the biochemical, to say so, connective tissue, the collagen of all kinds, and then other fibers, and those the glycoaminoglicosanes, so the fascia gels, right? At the fundamental level, they are very robust and kind of cheap and mass produced. But on the other hand, so that's good. But on the other hand, they are mass produced, but at the same time, their architecture, the functional architecture is very complex. So their material is simple and mass produced, right? So you see, that's material. And these integrations, how they work and so on, that's architecture. So, how the material gets combined. So, structure equals material times architecture, right? So you can get the same type of the, I don't know, practical outcome. You can make the, you see the simple example that I often use, right? See, if you have a very strong material, you can make like strong metal. You can make a very simple bridge, just put two metal plates and you can put heavy items on it, right?
Mm-hmm.
That means architecture here is simple, material is strong. Now, again, we move into Spain. What do we see there? You see a lot of the old bridges, they are like this, right? They are arched bridges. Yes? You've seen them?
Mm-hmm.
So, why they are like this? Because this bridge, the way that it's put into the architecture, these ones, they sort of go into each other, so it's when there is an extra load on this bridge, they lock onto each other. So, now, if you were to make it flat, it would break very easily. But, here, the architecture is up, material is down, right? So, it's not such a good, or this is a cheap, low cost, simple material, but thanks to the architecture you can make a good structure. So here a good structure is made thanks to the expensive material. Here it's made via good architecture. If we look back at nature, the general principle is minimize the costs of the material and maximize the savings from architecture. Yes? So, what happens during the period of crisis? That's where the architecture of fascia gets lost. Material is there, architecture is lost. That's why it's so difficult to detect. Right? So you see, in that respect, you look at the, them, even it doesn't show itself on an X-ray, it doesn't show itself as like that much of problem on the MRI, ultrasound, and so on. It's not specific enough because material is more or less the same. It's the architecture that matters.
Yeah.
Okay. Voila. Let's press. Ну что, ты поспала уже или ты еще?